We now look at composite angles, an angle that is made up of two components. We are often interested in applying trig functions to these angles, and we want to derive what the expressions are for these functions in terms of the individual components. To do this, we draw two right-angled triangles on top of each other, the hypotenuse of the top one being 1. Notice that there are three right-angled triangles here, one with the angle alpha, one with the angle beta, and one with the angle alpha plus beta. Looking at this final triangle, we see that the sine of alpha plus beta is equal to this opposite length divided by the hypotenuse, 1. Similarly, the cos of alpha plus beta is equal to this adjacent side divided by the hypotenuse, 1. If we can find these two side lengths, then we have our expressions. Our job is to use trigonometry to fill in any side lengths that we can. First, look at the beta triangle. Using trigonometry, we see that cos beta is equal to this adjacent side over 1, and so this side is equal to cos beta. We can use this in the alpha triangle, since this is the hypotenuse of that triangle. Cos alpha is equal to this adjacent side over the hypotenuse, cos beta, and so this side is equal to cos alpha times cos beta. Similarly, this side will be sine alpha times cos beta. Now we go back to the beta triangle and see that this opposite side must be equal to sine beta, since the hypotenuse is 1. Now we will imagine this side as the hypotenuse of a new right-angled triangle, which I will draw on here. If this angle down here is alpha, then this one must be 90 minus alpha. Since these three collectively add up to the 180 degrees of a straight line, and this angle takes up 90 of those degrees, this angle here must also be alpha. Using trigonometry in this triangle, we find that sine alpha is equal to this opposite side over sine beta, and so the opposite side is sine beta times sine alpha. Similarly, this adjacent side is equal to sine beta times cos alpha. Now we remind ourselves of the side lengths that will tell us the expressions for sine alpha plus beta and cos alpha plus beta. If we can express these side lengths, then we have expressed the trigonometric functions. This side is made up of two chunks which we know, sine alpha cos beta and sine beta cos alpha. Therefore, sine alpha plus beta is equal to sine alpha cos beta plus sine beta cos alpha. This side here can be thought of as this whole length, which we calculated to be cos alpha cos beta, take away the extra bit on the end, which is sine alpha sine beta. Therefore, cos of alpha plus beta is equal to cos alpha cos beta minus sine alpha sine beta. The first thing that you can derive from these is the expression for tan of alpha plus beta by doing the sine divided by cos. After some manipulation, we can write it in this form. The next thing we can derive are the formula for the sine and cos of alpha minus beta. All we need to recognize is that sine is an anti-symmetric function. So putting a negative argument into the function will output you the negative of whatever the output is with a positive argument. The cos function is symmetric, meaning the output of the function is the same whether the input is positive or negative. Now all we do is replace beta for negative beta in our formula. Any sine betas will turn to negative sine betas, and any cos betas will stay the same. The tan subtraction formula comes out like this. Finally, we can derive the double angle formulas sine, cos, and tan of 2 alpha. This can be done simply by setting beta is equal to alpha in all of these expressions, which give us the following formulae. We use all of these formulae in solving problems, but I have just shown that it is really only these ones worth remembering, since we can quickly derive the others.